Hi everyone, my name is Anusha. I'm a product manager in the Tensorflow team. I work on Tensorflow Extended, which is a production scale machine learning platform, and it's part of the Tensorflow ecosystem. So first I'd like to start with the difference between machine learning coding and ML engineering. So typically, when we talk about machine learning, we tend to think about training a model to accomplish a specific task. That's the meat of the word, right? But as you might know already, production scale machine learning is quite much more than that. As you can see here, typically the trainer code is less than 5% of the entire system. And majority of the time and code is spent in areas like data generation, augmentation, validation, which is a lot of it is related to data processing, and then post-processing like post model creation, which is model understanding, model validation, evaluation, and so on. It's not just that. Even as research makes its way into production, you don't want to re-implement a solution as it moves across phases. You want to have modular solutions that you can reuse as you come up with new ideas and work your way to get them to production. So there is a need for kind of a flexible yet robust system to apply ML to product. And I cannot reinforce enough that the ML code itself is a tiny piece of this entire puzzle. In fact, we tend to say that production machine learning is like 1% inspiration, which is your model code, and 99% plumbing or glue code. Let's take this example of enterprise machine learning, right, which reinforces the fact of what I talked about before. It took 3 weeks to build a model, and it's about a year, and it's still not deployed in production yet. There are many such stories which used to be common, even inside Google, until we started investing in ML infrastructure and ML platforms. So that brings us to what MLOps is. Let's take this scenario, right? In any company for that matter, let's say there is a group of modelers or data scientists who are working on a machine learning problem, and they're working on building the next best model for that particular problem. And then once they build that model, inevitably you have to work on scaling that solution. And typically that tends to be a handoff happening between the data scientists or the modelers to the operational folks, like that could be ML engineers or MLOps folks, which is why the name MLOps, who help with operationalizing this. So this communication and collaboration between the data scientists and modelers and the operations professionals is kind of what spurred this MLOps as a domain itself. This is similar to DevOps or data ops, but the focus here is improving the quality as well as increasing automation to make machine learning in production much simpler. And obviously, there are things to be noted like business and regulatory requirements. So let's see an example of how a production ML infrastructure looks like. There are 3 key phases here: the data prep phase, the model creation and model tuning phase, and finally the deployment or the rollout phase. As you can see, the data prep phase itself is quite intensive even before you get to the model creation at enterprise scale, right? So there are various steps involving data cleansing, data validation, feature pre-processing, and so on before you make the data that's available for training your model. And same happens with training as well. You need to think about training at scale. You need to be thinking about like tuning your model, figuring out the right hyperparameters, and being able to get the best possible model. And it just doesn't stop there, because now you have to think about how this is going to be deployed in a production system. Because once you train a model and make that available, the story doesn't end there for any production system. There is continuous maintenance, monitoring, and logging. And you often don't know, that there can be certain issues that can come up in production environment, because that type of data could be very different from the data that you were training your system on, training your model on. So deployment is also a very important area to be thinking about from a monitoring and maintenance perspective. So that brings us to TFX, which is a production scale machine learning platform built to handle the various phases of ML workflow we just described now. I just want to point out to TFX lineage. As I said before, we started investing in ML platforms at Google, and we've had quite an evolution in this space. ML platforms at Google is not a new thing. We've been building Google scale machine learning platforms for quite a while now, actually. As you can see, Sybil is a precursor to TFX, and it was started 12 years ago. So a lot of the designs, best practices, and other learnings that were collected during that time have been incorporated into the design of TFX. So TFX shares several principles with Sybil, but also augments it under several important dimensions. This made TFX quite popular, so it's one of the most widely used end-to-end ML platform at Alphabet. And it's also available on premises and on GCP. As you can see here, TFX powers several important Alphabet's bets as well as products. Not just in Alphabet, but as I said before, it's available as an open source solution. So we have several other external partners using TFX. I'd like to highlight one example from Twitter. They published a very fascinating blog post on how they rank tweets on their home timeline using TensorFlow. They talk about how they're using TensorFlow model analysis, which is one of the libraries that we provide to evaluate model on different segments, and TensorFlow Hub to share word embeddings. They evaluated several other technologies and production requirements, and they decided to go with the TensorFlow ecosystem. So similar to Twitter, several other partners shown here are using TFX. Now, we've talked about the word production quite a lot, at least in the first 10-15 minutes now. So what does production mean? I think there are two key aspects to production. First one is automation. Second one is scale. So what does automation mean in this context, right? You're thinking about automated processes for bringing in your data and validating it. Not just like data validation or data handling, but also training your model and serving that. So a complete end-to-end automation of your ML workflow. The second one is scale, because it might be interesting to first get started with a small data set on a laptop and build a model that can solve a particular problem. But when that same model has to be deployed in production, that becomes large distributed workload tomorrow. So these are two main aspects to be thinking about when we say production. And as you can see here, TFX, I would say, is a very layered platform which provides different entry points for users depending on what they'd like to use. First one is libraries, which you can see here for every step of the ML workflow that we just described before. And then there are components which are built on top of these libraries, which use these libraries. And these components, they understand the environment in which they operate in, and they consume and produce artifacts. I'll talk a bit more about what artifacts are and what our artifact storage layer looks like. The various components can actually be connected with one another to form what we call as a pipeline, which is an automated end-to-end workflow that you can set up. As you can see here, today I'm going to talk about the component layer, the orchestration layer, which is to orchestrate these components, and the pipeline storage or the artifact layer, which these components use to produce and consume artifacts. So let's first start with the components. TFX provides several standard components that map to various stages of your ML workflow. Let's get into the anatomy of a component first. What does a component look like? So a component typically consists of three key elements: the driver, the executor, and the publisher. Driver coordinates the job execution, which I said is for working with the orchestration layer to execute the workflow. The executor is the core logic which performs the work for that component, which can be like evaluation, validation, or training, and so on. And the publisher updates the ML metadata or the artifact layer that I was talking about, which is, for example, if you're training a model, the artifact would be the model itself that is being produced. Think of artifacts as results of the steps in the ML workflow. So if you look at this diagram, you can see what a component looks like. There is an input artifact, which is some kind of input that it consumes, does some processing, and produces outputs. And these inputs and output artifacts are referenced in the metadata store. Now, putting this in perspective with multiple components, you can see that each of these components will produce and consume artifacts, which can be results of the previous components' outputs, right? And consume that, and together they can work to form a seamless end-to-end workflow. Let's start with solid examples of what these components are and what kind of tasks they do. In fact, we provide several components out of the box. ExampleGen is the very first component. This helps you ingest data into your pipeline. So let's say you have CSV or TF records. So this helps consume several external files and services to generate examples. So this is the first step of bringing in data that you have into your pipeline so that you can start processing that data and then train your model. The next one is StatisticsGen, which is a component which generates feature statistics over both training and serving data, and which can be used by other pipeline components. It uses Beam to scale to large data sets. So this helps you understand your data set better, and helps you know what's probably, it just gives you like an overview of the various statistics of your data set. And then SchemaGen is an interesting component because it helps you understand the schema of your data. So it can specify data types for feature values, whether a feature has to be present in all examples, allowed value ranges, and other properties. So it will automatically generate a schema by inferring types, categories, and ranges from the training data that you have. One thing as we're talking through these components, I'd like to point out is not every component is compulsory when you put together your pipeline. You can put together a very simple pipeline in which ingests data, trains your model, and pushes that out to production. The various components that we provide here capture the ML best practices for putting a model to production, that if you use, it can ensure that you have all the guardrails in place. Next, if you look at the example validator component, now that you have generated statistics on your data, now you want to understand if there are any anomalies in your data. So it performs validity checks by comparing data statistics against a schema, which is generated by SchemaGen. It can help detect training serving skew by comparing training and serving data. And this is a very important, detecting training serving skew is a very important aspect for production, deploying models in production. This also can detect data drift by looking at a series of data. So for example, when you're looking at data, you might be able to realize that this data has some inadequacies because, for a data that's associated with all the records associated with trips, this is an example of a Chicago taxi data set, which is available for anyone to look at. And you can see that the data that is here is like the early hours of the morning. There is not much data about the trips. So it helps you understand like what are the inadequacies, or what are the things that are missing probably in your data. And you must have realized that you've not even gotten to training yet. That's kind of the reality of how the various steps happen in production scale machine learning. So until now, all that we've been talking about is data processing, and now we're going to talk about like feature engineering. So transform is a component that performs feature engineering on TF examples that we got through ExampleGen, and it can use the data schema which is created by the SchemaGen component. This makes extensive use of TensorFlow transform. As I said, these components are built on top of the libraries. TensorFlow transforms library for performing feature engineering on your data set. The types of transformations that you can do include like embedding, vocab generation, normalizing values, bucketization, enriching text features, and many more. Now, the interesting part here is you could be thinking, can I just do my transformations even as I get in my data and my storage, right? I don't have to do it inside a pipeline. Why do I have to do it inside a pipeline? So yes, you can transform your data however you like prior to running TFX. But if you do it within TensorFlow transform becomes part of the TensorFlow graph because transform produces a saved model. So this approach helps you avoid training serving skew. So what happens is this injects the results of the computation as constants and ops into the TensorFlow graph when you have it as part of your pipeline. And the resulting TensorFlow graph is hermetic because it contains all the information you need to apply the transformation. So what happens is the same transformations are applied consistently between training and serving that eliminates training serving skew. And finally, we come to trainer now, which can the trainer is used to train a TensorFlow model. What we have is what we call as generic trainer, which can be used to train any type of TensorFlow model, like use estimators, carers, or even low-level TensorFlow ops. And this talks about like the various types of inputs that you need to give to the component and it produces a saved model which is basically then going to be used by other components for evaluation. And as you're training, you can use TensorBoard to look at like multiple model runs and then be able to compare hyperparameters and so on. We also recently published a component called Tuner, which makes extensive use of the Python Keras Tuner API for tuning hyperparameters. So with a given data, model, and objective, the tuner tunes hyperparameters and emits the best possible result. And then once you're done with training a model and tuning it and getting the best possible model, you want to be able to evaluate this at scale. You want to be able to do deep analysis on the training results of your model. And you want to understand how your model performs on subsets of data. So the evaluator helps you do that. It's not just that. The evaluator does also another it has another interesting functionality called as validation, which when enabled, it helps compare new models against a baseline to determine if they are good enough relative to the baseline. So it evaluates both models on an eval data set and computes their performance on metrics like AUC and loss. And if the new models meet the developer specified criteria related to baseline model, the model is considered as blessed, indicating to the next component, which is pusher, to push the model to production. And this validation feature becomes very important in a production setting where you are continuously training models as new data arrives. And you want to put some guardrails in place because you don't accidentally want to push a model that's kind of suboptimal compared to the previous model that's in production. We talked about like Evaluator being a component for making sure the model quality meets the bar. Think of InfraValidator to guarantee that the model is mechanically fine and prevents bad models from being pushed. So this is also a component that we launched recently, which helps you to ensure that the model can actually be served in the serving infrastructure. And finally, the pusher component is used to push model to a deployment target during model training or retraining. And as I said before, the pusher relies on the blessings from the evaluator component to decide whether to push the model or not to your serving environment. We also have another component called as Bulkinferrer, which performs batch inference on unlabeled data. So this contains the original features, and the generated inference result contains original features and prediction results. So this gives you a fairly comprehensive set of out-of-box components that you can take and use for your ML workflow. But it's not just that. We do know that there are users who have advanced requirements, and their requirements don't fit within the realm of the components that we provide. So we provide ability to users to actually build their custom components and insert that into the ML workflow or the ML pipeline. So it looks something like this, where you can leverage the benefits of TFX because you can leverage as many components as possible, like standard components as possible. But at the same time, you can write your own custom component here. So custom components, some examples of where you can use custom components Custom components are can be used in areas where you want to build components that are tailored to meet your needs, such as ingesting data from a proprietary system, or probably you want to apply some data augmentation, or interface with external systems such as help desks for alerting and monitoring. So this gives you the flexibility to start adding components that make sense for your workflow. And we have three types of custom components. Python function components, which makes it easy for you to create custom components. You just use the annotation style and you write a function that's annotated with type hints. They describe the input artifacts, the output artifacts, and the parameters of your component. We have container-based components, which provide the flexibility to integrate code written in any language into your pipeline, as long as you execute that code in a Docker container. And we also provide fully custom components where you have the option to define component, reuse and extend a standard component if it fits within the realm of like just modifying the executor or the logic of the component. But at the same time, if you think even the inputs and outputs of the components are going to be totally different, you can design it from scratch. And we also provide some functionalities if you have to deploy in mobile and edge environments. The best part here is many of our components can be just reused out of the box for training your model. The two main changes that you have to do if you want to convert your model to be deployed in a mobile and edge environment would be to invoke our TF-Lite rewriter within the trainer, which can help convert the saved model into TF-Lite format, and then be able to evaluate that TF-Lite model at scale to ensure that the model quality metrics look good. And you can see code snippets for that here. So we spent a lot of time talking about the out-of-box components. I'll quickly go through the metadata store as well as the orchestration layer to see the value that they provide. If you think about the metadata store, it's a library for recording and retrieving metadata associated with the ML workflows. It's a very integral part of our TFX pipeline, but it's also designed so that it can be used independently. So what's in the metadata store? We talked a bit about this while talking about components. It has like type definitions of artifacts and their properties. So for example, depending on the component, these artifacts could be models, data, eval metrics, and so on. It also stores runtime config, inputs and outputs. So execution records of the components. This component ran at this time and it produced this input and this output. And then it helps you to recurse back to all inputs of a specific artifact. So an example of this is, let's say you have a model. Now you want to be able to recurse back all the way till the data that was used to create this model. This is a very powerful functionality. As you can see, one of the first things is it helps you to understand what data the model was trained on. In certain cases, this can also be a regulatory or legal requirement if you're putting a model to production. You might want to know, depending on the enterprise setting you are in, you might want to know what type of data spans this was trained on. It could be for fairness reasons or other factors. And not just that, it also helps with experimentation because you will be able to now compare different model runs, know what types of hyperparameters were used in each model run, and be able to see and experiment to understand like which data was used in which run. And another interesting use is also being able to carry over state from previous model runs, which helps with warm starting training. And not just that, it can also help cache intermediate results instead of recomputing every time. Think about like having to have a component rerun every time and recompute results. Rather than doing that, you can just cache and reuse the previously computed value. So metadata has been a very powerful functionality that can help with experimentation as well as for lineage and artifact tracking as you are managing your ML workflows. Think about the case where you have like thousands of models that you're creating or hundreds of models that you're creating and you want to be able to keep track of the inventory and the artifacts associated with it. And finally, we have the orchestration layer. Before talking about like the orchestration layer, let's just touch a little bit about the type of orchestration styles that you have. We talked a lot about these components, right? There are these components that can be put together, and these components have to run. As they run, they will produce and consume inputs and outputs, which will be stored in this metadata layer or artifact layer. Now, there has to be some kind of a workflow management system that needs to run these components. How will that ML workflow management system look like? There are two possible models for this, like a task-driven system versus data-driven system. Both of them are powerful here, right? So let's take task-driven system where you want to run a pipeline or set of components or an ML workflow end-to-end, and you want to do this like probably once every week, right? You want to schedule this at a specific time and you want to run this every week. That's a clear example of a task-based system. Or you might want to continue to experiment with that pipeline. So each time you want to manually set up the pipeline and rerun the pipeline, get the outputs and continue to work on that. So those are all like very task-driven approaches. If you think about a data-driven approach, you can think of a case where model freshness is quite important. So there'll be new data coming into the system. So this shows like the true power of automation, right? There'll be new data coming into the system time and again, and like at a particular frequency. And as new data comes in, you want to be able to train the model based on that new data, because model freshness is an important category, and be able to push the model to production. And this is where some of those components that we talked about, like the validation part of the eval component, InfraValidation, all of this ensures that you're able to continuously train and push a model in an automated manner without having to, constantly like monitor it, especially if you want to train it multiple times a day. So what does TFX provide in the open source world for orchestration? So we have this concept called as bring your own orchestrator, which means you can plug in orchestrator of your choice, and we provide like 2 or 3 choices here. The first one is we have Airflow as a possible workflow management system that you can use with TFX components. We also work with Kubeflow pipelines, so you can use TFX components. You can use the ML metadata layer, use Kubeflow pipelines DAG runner or the orchestration system to execute the workflow. If you want to run this locally, we also have a Beam based execution so that you can use a Beam runner to execute this locally. So that brings us to how you run TFX pipelines on GCP. So as I said before, we work with Kubeflow pipelines in a layered manner. So we have TFX components, we use Kubeflow pipelines as the DAG runner, and then we execute our components on GCP. This gives you a very high-level view of the layered architecture that we have on running like TFX on Kubeflow pipelines on GCP. This is a much deeper stack view of the layered architecture of TFX on KFP and how it executes the workflow itself. As you can see, TFX has pipeline templates or examples that help you get started with standard components easily. And TFX is also continuing to add support for many custom components. If you want to just start with a very custom pipeline, you could start with just starting with the KFP SDK. So to summarize what TFX provides, it provides several out-of-the-box components that we discussed in detail today for your production needs. It provides extensibility with custom components. And then we provide bring your own orchestrator or flexible orchestration for orchestrating these components to realize your ML workflow. And we provide an artifact layer so that you can keep track of your ML workflows better. And if you're interested in checking out TFX, check out tensorflow.org/TFX. And these are links to our repo and community. So that brings us to the end of this talk.
Great, thanks, Anisha, for the great talk. And let's go to Q&A. Can you click Q&A? And I think we have a few questions For other attendees, if you have questions to speakers, please post in the Q&A. We are go over the Q&A right now.
Sure, I can start addressing some of these questions. So, are the component libraries, are they extensible for customization? Yes, we are increasingly working on making many of these libraries customizable, like the model analysis libraries. We are working on, adding like hooks so that you can extend these libraries and customize them to their needs. I would highly recommend checking out our custom components to see how you can start extending our executors and changing our executors and customizing that according to your needs. And another question was, another end-to-end ML platform, it has extensible customizable architecture. You mentioned that TFX can use Kubeflow pipeline as orchestration framework. What are the advantages of TFX compared to Kubeflow? So the main benefit for TFX is the out-of-the-box standard components that capture the ML best practices that we provide, right? Along with the ML metadata or the artifact storage layer. So what we provide is these templates that make it easy for you to get started with building your pipeline, because you don't have to reinvent the wheel, or you don't have to start writing custom components for every step of your workflow. So if you're someone who's like, give me a set of like common examples that I can get started with for my classification or regression problem, and I just don't want to reinvent the wheel, then TFX helps you to a great extent with that. That being said, we're also increasingly focused on customization, so that let's say you can reuse like 4 out of 5 components for a pipeline that you want to build. And the 5th component has to kind of be a custom component because there is no out-of-box component. So we want to start supporting those workflows as well. So that's one of the reasons why we are adding more customizations to TFX. In the KFP world, I think there are a lot of reusable components, and it starts with a custom component as the base, if I understand correctly. So those are like the differences I see in that space. And is there AutoML integration with TFX? So in our components as of now, we don't have AutoML integration. So I'm assuming that this is referring to the cloud AutoML APIs related integration. But that's actually a great idea. So we should probably be thinking about like how can we start providing AutoML APIs access. But as of now, in our components, we don't have like AutoML specific components yet. How does this work together with distributed processing technologies like Spark? So right now, our structure is focused primarily, it works with Beam, right? With Spark, I think there is quite some work to be done for us to be working effectively on Spark. So I would say we're still not 100% there yet.
I think there are a question in the chat. Do you want to take a look, or I can read to you?
Sorry, which?
In the chat.
Yeah, I'm looking at the chat. I'm trying to see which question.
I think the last 2, 3. Do you see quite a long one? How does the config help towards data computer hyperparameters, feature engineering, performance metrics? Did you see that one?
Could you elaborate on that question? Sorry, I didn't quite understand the question. When we say config, are we talking about like the specification of the ML workflow itself?
Okay, while we are waiting for that, we have 1 more minute. If anybody have questions for Anisha, you can post in the chat or in the Q&A. We can get it answered.
Yeah, that's a great question. Can GANs be used in this domain? It depends on the kind of GAN that you want to productionize and the kind of model that you want to build, the type of data format that you want to use. In fact, we recently just published an interesting blog post of how we use TensorFlow to transform voice to an instrument. So that's a very interesting blog post that we have been doing for Indian Independence Day. So that's kind of closely an example of how we've used TFX for productionizing like a GAN type of model. I can just link to that blog post in this chat.